Hello and welcome to another video by Econo Insight. In this video, we're going to discuss the Solow growth model with a numerical example. So here's the question that we are going to solve. This question is adapted from Mankiw Macroeconomics. If you want to check out the original question, refer to that textbook, but this question has been modified for the purposes of this video. So you can screenshot it, and the question is also available in the description down below. Now let's solve A. A asks about, does this production have constant returns to scale? Well, the simple answer is yes. Because why? Because 0.4, right? So this actually is written by like this, L 0.6 equals Y, right? So you don't get confused. So the capital share of income and the labor share of income, which is 0.4 plus 0.6 equals 1. The rule of thumb is that when the capital share of labor and the capital share of income and the labor share of income equals to 1, then the production function has constant returns to scale. So that simply answers it. And now B, what is the per worker production function? First, remember that in the Solow model, everything is in what you call as per worker terms. So everything is per worker terms. So now let's find the per worker production function, right? So our production function is here 0.6, sorry, 0.4, and labor, the share of income of labor is 0.6. That is from the question above. Now let us multiply the production function every component by z. So we let z equal 1 over L. So this is, we are making sure that the production function is in per worker terms. So zy equals z, right? K 0.4, then zl 0.6. Now let's expand that. I'm going to move it to the other page so it's easier for you guys. Okay. So here's the thing we just derived. Now, we said earlier that z equals 1 over L. So 1 over L multiplied by y, right? Brackets, again, put brackets. Brackets are your friends. Then power of 0.4, then 1 over L times L 0.6. Now we see that this equals y, big Y over big L, and this equals K over L. Don't forget the power, which is 0.4. And here, interestingly, because if we put L over L, that is essentially 1, right? So we just disregard that. So our production function now is this. And just to make it more intuitive here, Y over L is actually output per person. And that is what we know as GDP per capita. So that's, and K over L is capital per capita, or to make it more simple, it's capital per person. So this thing basically tells us that output per person is a function of capital per person. So now let's write that. So to simplify things further, we write Y over L as little y and K over L as little k. So if you see K, little k, or little y in the Solow model, remember that is not capital or Y is not output. Y is output per person, and K is capital per person. So now let's write it all down. So little y, output per person, is K, capital per person, to the power of 0.4. So that is our per worker production function. That's very interesting. And now, moving on to question C. Question C says, assuming no population growth or technological progress, find the steady state capital stock per worker, output per worker, and consumption per worker as a function, don't forget this, as a function of the saving rate and the depreciation rate. This might seem a little daunting at first. It seems scary, but now let's solve it step by step. So first, it asks for the steady state values. And remember, in the steady state, savings equal depreciation, right? Like when savings, so when savings equals depreciation, the output per person no longer grows, and because the capital per person no longer grows. That's why when savings equal depreciation, you have reached steady state. Now let's write that mathematically. We know savings is a function of output, right? And depreciation there's a depreciation rate in the country, and we multiply that by the amount of capital. If you're not familiar with this, you should be familiar first. It's what you call the equation of motion in the Solow growth model. So when savings equals depreciation, then capital per person stops growing, hence output per person stops growing. So make sure you're familiar with this before I explain. So yeah. So now we know that our y here, right, is k. So little y is basically this. It's the same thing, yeah? So we know that f of k is k to the power of 0.4. Again, put brackets, and equals depreciation. Alright? So now let's manipulate this. If we move the depreciation to the left-hand side, and we move the capital to the power of 0.4 to the right-hand side, we get this. And if we simplify this, it simply means this, right? But now we want to know the capital, right? We don't want to know capital to the power of 0.6. We just want to know what's capital. So now that needs little math. So let me rewrite it in a more nicer way here. Now, in order to isolate this capital, we must multiply it. We must put a power of the reciprocal here. So then, give me a second. If you see here, by putting the everything to the power of 1 over 0.6, we can cancel it, right? So k 0.6 over 0.6, right, is 1. So we can just cross that out, and we get k. We get here k is equal to savings over depreciation to the power of 1 over 0.6. To make it more clearer, if you calculate this in a calculator, this will become 5 over 3. So that's the same thing. So now we have derived our steady state capital per worker as a function of savings and depreciation. So that's one job done. If you don't understand it, repeat this. Now we want to find the steady state output per worker, right? So we know from the per worker production function that we have little y equals little k to the power of 0.4, right? Now, we now have derived our k, right? Our k, as we have derived in the previous page, is savings over depreciation to the power of 5 over 3. So it's simple. Now we just simply write everything, savings over depreciation to the power of 5 over 3. Then since our production function is k to the power of 0.4, then we put another bracket. We put it to the power of 0.4, which is 4 over 10, right? And now we just solve this part here. 5 over 3 times 4 over 10 equals 20 over 30, which is 2 over 3. So our steady state up per worker is little y is equals to savings per depreciation over depreciation to the power of 2 over 3. So there we go. Now we have solved it. We got the steady state output per worker. For the last bit, what is the steady state consumption per worker? We know that consumption is C y minus I. Why is this? Because in the Solow growth model, our output y is a function of what we consume and what we save, which is what we invest basically. So y is consumption plus investment. So as we're trying to find steady state consumption per worker, we just switch it. C equals Y minus I. Okay, and everything, remember, is in per worker terms. So Y is output per person, consumption is consumption per person, and investment is investment per person. Don't forget that, very important thing. So now we got our Y from above, which is savings over depreciation to the power of 2 over 3. And investments, remember, investments in the Solow model is equal to the savings. Don't forget that. So it's essentially savings, the savings rate, which we do not know, right? Multiplied by our, what do you call this? Our output per person in steady state, which is above, which is S over depreciation to the power of 2 over 3. So that is our consumption function. But now we want to simplify this so it's easier to read. So C, we factorize it, is 1 minus S. We can take that out and simply put the remaining here, S over depreciation to the power of 2 over 3. So that is our steady state consumption per worker. I know the steady state consumption bit is kind of tricky, but yeah, so that's how to solve it. Repeat over and over if you don't understand the video. It helps. Trust me. And the last part is essentially here. Assume that the depreciation rate is 15% per year. What capital stock maximizes consumption per worker? What saving rate maximizes consumption per worker? So if you see something that maximizes consumption, that is referring to the golden rule of capital, right? Golden rule of capital is a condition where the consumption is maximized in the economy. So we directly go to the condition of the golden rule, which is MPK equals depreciation. MPK is the marginal product of capital equals to depreciation rate. So in a if you forgot, just a little refresher. So this is our output function, and this is our depreciation. Sorry, it should be a straight line. Let's say depreciation. My drawing is not that good, but this must be parallel to this so we can maximize the consumption. Okay, so back to the condition. Marginal product of capital must equal depreciation in golden rule. So first, you must find, we got the depreciation rate by the question. It's given, it's 15%. We write it as 0.15, but we do not know the marginal product of capital. That bit, we need to do it ourselves. So let's find the marginal product of capital. Well, that's relatively easy. We have little y, that's our production function, is k to the power of 0.4. So we use a bit of calculus here. We differentiate it. So now, so MPK, okay, we differentiate it here. So now let's differentiate this, right? So then MPK equals 0.4 del k to the power of minus 0.6. So now we got that. And we simply need to make, let me just put it in the next page. We need to make what we have found here, 0.4 k to the power of 0.6 equals to the depreciation, which is 0.15. So this can be rewritten as 0.4, since it's a negative power, put it downstairs, and that equals 0.15. So we just manipulate it. 0.4 equals 0.15, little k to the power of minus 0.6, right? Just to the power, sorry, this should be not negative, this should be positive, 0.6, and that is 0.6. Okay, so k 0.6 equals to 0.4 over 0.15. Now again, we did what we did earlier. To find k itself, we multiply the power by the reciprocal, so 1 over 0.6, right? Then 1 over 0.6 here. This cancels out because that equals to 1. We don't need to write that. And this here, this bit here, equals to 5.128. So, in conclusion, our K is approximately 5.128, and this is the capital stock that maximizes consumption. And don't forget, in golden rule, we put K star, just some notation for you to have. And now, lastly, although it's long, I know, is to find the savings rate that maximizes consumption. So that is simple. That is then, as we know, our capital stock that maximizes consumption, which is 5.128. To find the savings rate, we pull back the equation of motion that we have previously, right? And we just plug in the values. So this equals K 0.4, 0.15, and K here we have gotten it from above, which is 5.128. So then S is simply, this is just simple math over K to the power of 0.4, but remember K again is 5.128, so S equals to 0.15, 5.128 over 5.128 to the power of 0.4, and plug that all into a calculator, and our savings rate is 0.4, which is 40%. So a savings rate of 40% maximizes consumption. Some of you might wonder, why do we have to bring up this equation of motion again? Because we need to find the savings rate, right, that intersects that intersects with the depreciation here. So we need to find that. So that is why. So it's easy now. Since we have found our capital stock, right? We just need to find the savings rate here. That's why we use the equation of motion. If you are still confused of what the equation of motion is, make sure you master that one first, because or else it's hard for you to understand this question. I hope it helps. I know it's complicated, but keep trying. Thank you. I hope it helps.